Europlanet IDIS teams have developed an access protocol to planetary science data named EPN-TAP, which means Europlanet Table Access Protocol. You will visualize an example of what can be performed with this protocol through the presentation science case, Exploring Exoplanets. An exoplanet is a planet orbiting a star different from the Sun. The first extrasolar planet was discovered in 1995 around star 51 Pegasi, at about 40 light-years away from the Earth. Since 1995, the number of discovered exoplanets has significantly grown, up to almost 1,000 today. First of all, we will work from the Europlanet client webpage. From this webpage, we are about to ask all VO services the same question. What do you have concerning exoplanets? Thus we select exoplanet in the target class section and then we send the query. We see that one catalogue gives a positive answer, the Exosolar Planet Encyclopedia at Observatoire de Paris. To distinguish between exoplanets and brown dwarfs, which are very low mass stars having a faint luminosity, by convention, the Exosolar Planet Encyclopedia sets an upper limit of 25 Jupiter mass for exoplanets. Secondly, we intend to display exoplanets data. We will use TopCat, a client well adapted to this task. By clicking on TopCat here, the program will start. We authorize it to start and the TopCat window appears. Now we need to transfer data from the Exosolar Planet Encyclopedia to TopCat. The VO will help us once again with a protocol called VO-SAMP, Simple Application and Messaging Protocol, which permits to transfer automatically the entire exoplanet catalogue to the client TopCat. Once the loading is completed, we see the Europlanet table, corresponding to the selected catalogue in the table list section of TopCat. By clicking on this icon, we can browse the catalogue content. The catalogue, visible here, contains physical parameters for all detected exoplanets. Let's see what these parameters correspond to, with some plots for helping. Firstly, we will investigate exoplanets' spatial distribution, displaying the entire exoplanet catalogue on the celestial sphere. To do so, exoplanets' coordinates have to be indicated to TopCat. In Europlanet protocol, coordinates are noted C1 and C2, so we ask TopCat to display on the sky C1 and C2. All the known exoplanets appear automatically on the celestial sphere. We can see an accumulation of discoveries in this region that we expected exoplanets to have an isotropic distribution. TopCat will allow us to understand the origin of this concentration. By clicking into this accumulation of exoplanets, we have access to the part of the catalogue corresponding to the planets of this region. We can note that they are referenced by Kepler. The reason is that they have been detected by the same spacecraft named Kepler. This region is the observational zone of Kepler, and that is why many exoplanets have been detected here. On this figure, you can see the observational field of Kepler. TopCat will help us to make other interesting discoveries. Let us study the application of Kepler's third law of planetary motion to exoplanets. The astronomer Kepler found out in 1619 the relation between the square of the orbital period of a planet around the Sun and the cube of the semi-major axis of its orbit. The latter is the half of the major axis of the ellipse corresponding to the orbit of the planet around the Sun or another star in the case of an exoplanet. To find this relation, he observed the planets of our solar system and used the observations of his predecessor Tycho Brahe. Although Kepler didn't make numerical applications with those parameters because he missed some elements, he published the famous third law. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. In other words, their ratio is constant for a given planetary system. What will TopCat show us if we look at this relation? We will plot the semi-axis versus the period, and to take into account the power laws of the semi-major axis and the period in Kepler's relation, we will choose logarithmic axes. As a result, we see this straight line which confirms that Kepler's law applies to exoplanets as well. This is not surprising because gravitation works the same way in every system. We can study other properties like the angular distances of exoplanets to their corresponding stars. We will plot this parameter for all detected exoplanets versus their discovery dates. We see that the range of angular distance of the detected exoplanets widens with time. We detect planets more and more distant and also closer and closer to their star. We may believe this is due to the fact that we simply detect more planets over time. Actually, it is only right for planets close to their star. We refer to the European Spatial Agency website, which presents techniques to detect exoplanets. A first and indirect method analyzes the radial velocity of observed stars, looking for periodic variations. This technique led in the past to the discovery of double stars. This method is actually used to observe exoplanets orbiting closer to their star. The planet is detected when enough observations are accumulated. Most exoplanets have been detected by this method. A direct method of detection exists and improves continuously: the imaging detection. It consists in directly collecting the light of the planet and requires measurements with a very high angular resolution. Improvements of imaging methods allow to detect planets more distant to their star. This can explain what we observe on the plot. You can see here the planets B, C, D, E of star HR 8799 detected by direct imaging. Let us look at another parameter, the mass of exoplanets. As previously noted for the range of angular distances, the range of the mass of detected planets increases with time. This is mainly due to the decrease of the lower limit. It is now possible to detect very small planets which generally orbit very fast around their star due to improvements of the technique of radial velocity. Finally, we see that it is possible to interpret the observations and to infer important information about the exoplanets by studying their physical parameters. This is done in a simple way using tools of the virtual observatory applied to planetary data made accessible by the Europlanet Table Access Protocol. Thank you for your attention.